So we saw this set of activation functions. Now we will also talk about what is a loss function and a cost function. In many cases, you would notice that the loss and cost are interchangeably used, but I would like to separate this out a little bit. Okay. The loss function is computed based on the mean square error. You know what is the output that you are computing and what is the target. Okay. So, here this you know now very well, right. So, we have the predicted value computed using this equation 2, and W naught is your bias and x is the input vector and W is the weight vector, and if y is the target that we are looking at, the loss is computed using the mean square equation as follows. Okay, so the idea is to minimize this loss, correct. So, when it becomes negligible, we can say that we can stop, we can tell this system that stop the iteration. Okay. The cost function is a little different. If you look at the difference here, let us talk about the loss function is a prediction and the is a function of prediction and target values, right. In the cost function, what we do is we just call this as the function of model parameters and bias. This theta represents your W and the bias. This is the parameter that these are the parameters we are trying to estimate, right, in the model. So, this is going to represent the parameters that are going to be estimating. So, it is usually represented as j theta. Okay. It is very similar to what we saw earlier, but in this case this will represent only the computation is very similar to what we have done in the loss function. Okay. But there is a slight change in the representation here. And another one, I think I spoke about this a little bit earlier, we would be using gradient descent in order to find the local minima. I will be talking about the local minima most of the time. In many cases, you know, the ideally this is what we expect, and then our minimization problem comes down in the negative slope and then finally reaches the end point here. The end point. Okay. But in the so you may also get something like this, or you may find the error function going like this. In most cases, you know, when you follow the gradient descent, ideally I want this to come down the slope, and then finally when it reaches the minimum, there will be no more change. That is when, you know, the value of the gradient will become very small or it will be equal to 0. We say that, okay, I reached the end of my weight computation. Okay. So, that means I can stop my iteration. We do not get into that many times. We will come here and then get to this point and think that this is my minima, but my global minima is somewhere here. Since the algorithm will start finding the increase in the error value after some point, you will think that, okay, it is not doing good, let me stop here, and we call this as the local minima. Okay. So, we will not worry about this at this point in time. I just thought I would tell you about what is local minima and global minima. Gradient descent is usually used to get to the minimum value here. Okay. So, how do we get to that value? Using the iterative process, where we keep changing the value of the weight based on the cost function. Okay. And then we have seen that eta is also your learning parameter, which is adjusted to either 0.1, sometimes it could be even 0.1, 0.01 or 0.001, depending on your application. We normally start with the initialization using random values. All the weights are adjusted to have random values, and then the weights are adjusted in the direction of steepest descent, or in the direction that decreases the cost function. And then we know that how to compute this. We'll talk about this when you go into the artificial neural network, where we have multiple layers. Okay. And assume that for now that we're going to be using gradient descent algorithm, that's going to take us to the minimum, or let's call it as the minimum of this function. Okay. Again, you will see representation of the same thing in different ways. This is a one-dimensional representation. You will also see the quadratic contours. It is seen from the top. Okay, so what we have is a side view of this function. This is seen from the top. You will see the iterative process moving in from or sliding into the minima from here. So it is like this. Okay, and when you see from the top, you will see the contours in this fashion, and then we are coming down from here to here to here to here, and that's what is shown here in this fashion. So it's an iterative process, and also you can see that the decision function also is moving slowly and steadily closer to the actual one, which is provided as plus corresponds to the original data point, and that could be obtained by an iterative process starting from this. So initially you have some random values. In this case it is 0. I think we spoke about that earlier.